Hi again, everyone. Today we're going to talk a little bit about so-called ODEs, or ordinary differential equations. Now, this video may be considered as a very basic introduction to the subject. So we're going to ask and answer what is an ODE. We're going to motivate the topic. We're going to look at different types and orders of these ordinary differential equations. And we're also going to discuss the idea of a solution. Now, these particular types of ODEs and their solution methods will be covered in other videos. So this video is just a real basic introduction to ODEs and their solutions. Okay? So, the first and important question is, what is an ordinary differential equation? Well, basically it involves two things. We have the derivative or derivatives of an unknown function and an equal sign. That's the basic setup of an ordinary differential equation. So let me give you some examples. Okay, so here the y dash would mean dy dx. So here's an ordinary differential equation. Here's another ordinary differential equation. Here we have a second order derivative and a first order derivative present, and also y, the unknown function. Here I've used the D type notation. Okay, so when we write down an ordinary differential equation, sometimes we use the dash notation, sometimes we use the dy dx notation. We use them interchangeably. Now, like most equations, what we want to do with these ordinary differential equations is to solve them. Okay? And we're looking for an unknown function in this case that satisfies the differential equation. Okay, so at school, when you solved, for example, algebraic equations, quadratics and things like this, and found the roots, you were looking for numbers as your answer. For these ordinary differential equations, we're looking for functions, like, for example, x squared or 2x plus 1 or e to the x. Okay? All right, now, we call these types of equations ordinary differential equations because regular, ordinary derivatives are involved rather than partial derivatives. Okay? Now, a really important point here is motivation. Why should we spend time studying these ordinary differential equations? What are their benefits and how can they help us? Well, you may have heard of the following equation from basic physics. Okay, Newton's second law. If we use this basic equation and relate it to differential equations, then this is one way how we can actually produce differential equations from certain modelling situations and phenomena. Okay? So basically, Newton's second law means that, or it says that when a body with mass m is acted on by a net force F, the body has an acceleration A. Okay, so we're going to use this equation to form some sort of differential equation based on modelling. Now, from basic calculus and basic physics, we know that the velocity v of the body and its acceleration is related by this equation here. And in addition, if the net force depends, say, on the velocity, which it does in many applications, then what we can do is go back to Newton's second law replace f with f of v, and replace a with dv dt. So I end up with something like this. Now, if I can, this is a differential equation in v here. Okay, I can rearrange it to form this, and then we can try to solve it for the unknown function, the velocity function in this case. Now, a particular net force might be something like the following. Here, m is the mass of the body, g is the gravitational constant, k is a constant, and v, of course, is the velocity. And this particular net force arises when we analyse a body falling under gravity that's subject to wind resistance that's proportional to its velocity. Okay? All right, well, that's a little bit of motivation, but let's go a bit further. How are differential equations useful? Well, by solving a differential equation, we can, hopefully, make some predictions about the phenomena, the process that we're modelling. Okay, what we would like to do is look at our system, our phenomena, model it using a differential equation, solve that differential equation, and that will allow us to make future predictions about the future state of the system. Okay, so that's the basic idea. The important thing here, by using and solving differential equations, we can make precise predictions about the future behaviour of our systems or our models. Now, some differential equations are very, very difficult to solve, especially the so-called non-linear differential equations. And even if we can't completely solve a differential equation, we may still be able to determine useful properties of the solutions, so-called qualitative information. And this is a very, very interesting field in its own right. Okay, so that's a little bit of motivation. Let's talk now about what we mean by a solution to a differential equation. Okay? The big question is, throughout this section, when given a particular ordinary differential equation, how can we find the solution? Okay, what methods can we develop and apply to calculate or extract the solution? However, before we get to that, what do we mean when we say a solution to an ordinary differential equation? What do we really mean by that? Well, the short answer is the following. Basically, a solution to a particular ODE is a function that's differentiable and that satisfies the given ODE for x in some interval. Now, more formally, suppose this is our differential equation here, where f is some function of two variables. Now, that f has a domain, D. Okay, and more formally, we call a function y, equals y of x, a solution to this problem on some interval, I, if for all x in that interval, y satisfies this problem. So in other words, y is a differentiable function for all x in this interval, and this equation holds for all x in the interval I. And secondly, the graph of y, in other words, these sets of points, are in the domain of f. Okay, so those 2 points guarantee that you have a solution to a given ODE. So let's look at this a little bit in more detail. All right, here's an example. This is one I've prepared earlier. Here's our differential equation. dy dx equals 2y plus x. And the claim is that this function here, y of x equals minus a half x minus a half, is a solution to this problem for all x in this for all real numbers x. So in other words, the interval would be minus infinity to infinity. Okay, so here we have an infinite interval. This may not always be the interval, though, that we're interested in. All right, so let's go through and verify that this function really is a solution to this problem on this interval. All right, so the first thing we're going to do is look at the domain of f. Well, I can input any x and any y into here that are real numbers, and this right-hand side will be defined. Okay, so the domain of f is r squared. Now, for all x in this interval, we're going to now look at the graph of this function here. Well, it's these set of points, and you can see that both of these, for any real valued x, this is going to lie in r squared. So the graph does lie in the domain of f. Okay, for all x in this interval. Okay. All right. Also note that this is a differentiable function for all x in this interval. All right. So the next thing we want to do is show that this function actually satisfies the equation. So to do that, we consider the left-hand side of the differential equation, the right-hand side of the differential equation, and then compare them and show that they're actually equal. All right, so the left-hand side of equation 3 is just dy dx. So if this is our y, then we differentiate it here, and we get minus 1/2. Now the right-hand side of our differential equation is just 2y plus x. So I take my y, I substitute it in here, and then again I get down to minus 1/2. So if we compare the left-hand side and the right-hand side, we see that they're equal for all x, for all values of x in this interval. And therefore, the ODE 3 holds for all x, for all real numbers x. So we can conclude then that this function is a solution to the ODE 3 for all x in this interval. Okay. Here's a couple of independent learning exercises for you to do. The first question I'm going to pose is, can you find another solution to that particular differential equation that exists for all x in the real numbers? And secondly, can you show that this function x squared is not a solution to that previous ordinary differential equation for all x in this interval? Okay, and to show, I'll give you a hint for the second part. What you want to do is go through the same process as the previous example and show that the left-hand side and the right-hand side are not equal for all x in the set of real numbers. Okay, but this is more difficult. Okay, but I'll leave that for you to do. All right. Another important concept in the theory and application of ordinary differential equations is the idea of order. Okay? Now, the order of a differential equation is the highest derivative that appears in the equation. Okay, so you can have first-order derivatives, second-order derivatives, third-order derivatives. What you do is you look at the ODE and you identify the highest order derivative, and that will be the order of the ODE. And why is this important? Well, the order of an ordinary differential equation plays a crucial role in solving these types of things. Okay? So let's have a look at some examples. All right, if we look at this first equation, you can see, all right, well, I've got a dy dx in there and no higher order derivative. So this would be a first order differential equation. If we look at this second equation, you can see I've got the highest derivative in this equation is the second order derivative. So this would be called a second order ODE. If we look down here, again, the highest order here is first order. The highest order here is third order. The highest order here is second order. Okay? Now we're mainly going to concentrate in this video on first order differential equations. Okay? This section is all about solving first order differential equations. Okay. Another important idea is the concept of an initial value problem. Okay, so in an initial value problem, sometimes we call this an IVP for short, we are given an ordinary differential equation and we're also given some extra pieces of information. Now, in particular, we're given the value of the unknown function at a particular point. Okay? And the extra pieces of information are known as initial conditions. So let me give you an example. Here we're asked to solve the following initial value problem. dy dx equals 2x subject to y of 0 equals 1. So here we have the ODE. Here we have the initial condition. Okay, so we've got to a stage where we're faced with an ordinary differential equation and some extra piece of information. How do we solve this? Well, if we look carefully at this ordinary differential equation, it's first order, and the right-hand side only involves the independent variable, in this case x. So what we can actually do here is integrate both sides with respect to x. That will get rid of the dy dx, and then perhaps we can use the initial condition in some way to clarify the solution. So let's do this. So our ODE has a right-hand side that only involves the independent variable x. Thus, integration yields the following. All right, so what I'm going to do is I'm going to integrate both sides of this ODE with respect to x. Okay, over here I can cross off these dx's and integrate. I'm going to get plain old y. Over here I'm going to get x squared, and I'm going to put a constant of integration in there. Now the constant of integration will cover both constants of integration from both sides. Okay, so it's not a big deal there. So what this means is that this general function here satisfies this differential equation, because if I differentiate this, I always get 2x for any constant c. Now, notice that we haven't used the initial condition yet. What the initial condition allows us to do is to find a particular value of this constant c, this constant of integration. Okay, so now what we do is we apply the initial condition to find our constant c. So we know that at x equals 0, the value of y is 1. So let's use that information I'm going to go to my general solution and substitute in x equals 0. So this will disappear. So if we look at this equation here, we know that c must equal 1. So what I can do now then is return to my general solution, substitute in c equals 1, and write down a so-called particular solution. It's going to be x squared plus 1. Okay? So note that the method was first involving the ODE to find a general solution, and then we applied the initial condition to form a particular solution. In other words, we got a particular value for our constant of integration. Okay? Now, I must admit, this is a very easy problem to solve. Okay? And when we move on to other types of equations, it's going to be much more difficult. All this really required was an integration method, right? So that's a little bit about the basic introduction to ordinary differential equations. One good technique, when you reach this stage, how can I check that actually I've calculated the correct solution? Well, you can go back to your ODE and go, does this function satisfy this ODE and this initial condition? And another good question, of course, is what is the domain of this function? Here this is defined for all real numbers x. Okay, so the interval that this function is a solution to this initial value problem is the set of real numbers. Okay? So a good technique is to always check your answer by differentiating it and substituting it into the ODE. Does the ODE balance? All right, well, in other videos we will look more at more difficult ODEs